This is going to be a brief review of how we determine the order of a reaction when we are studying chemical kinetics in order to know how a change in concentration of each of our reactants is going to impact the rate of a reaction. Now, in order to determine the order of a reaction, you are only ever going to be able to do this experimentally. And I feel quite sure you're going to get some practice with this in lab, so you can actually relate what you're learning in the lecture to what you're doing in the lab, which will really help you. If it's an experiment, we're going to collect data. And here you see a table where we run a series of experiments, 1 through 4, and we vary the concentrations of A and B in order to evaluate what is happening to the rate of the reaction. The name of the game here is figuring out our rate law. And since we want to determine the order of the reaction in particular, we're going to be looking at our exponents. We're going to be trying to figure out what is X and what is Y. So how can we do that? Well, there is a very good and constructive strategy to figuring this out, which is looking for where one concentration is varied for one reactant while the concentration of the other reactant is held steady, and asking what happens to the rate. This is going to tell us the order of our reaction. So let's analyze our data that we're presented with in this table so that we can see exactly what is meant by this strategic outline. So between experiments 1 and 2, you may notice that the experiment of A has been doubled, while the concentration of B has been held constant. That means we're effectively taking B out of the picture, and it allows us to explore the impact of a change in concentration of A on the rate itself. So what do we notice? We notice that if the concentration of A is doubled, the concentration of the rate is quadrupled. This is a simple ratio, right? 1 divided by 0.5 is 2, that's a doubling. 0.008 divided by 0.002 is 4, that's a quadrupling. Now, alternatively, we could look at a different set of experiments. Let's say we look at 2 and 3. So now notice we're actually doubling the concentration of B while we're holding A constant. This is effectively taking A out of the picture and exploring the impact of changing the concentration of B on the overall rate. So this is an interesting one because notice that we double B, but that we actually don't impact the rate at all. So now we're going to turn our attention to how can we use that data in order to determine exponents. Exponents are what tell us the order of the reaction. So if we tackle A first, so let's look at this part here. We're going to tackle A, and we're going to compare, as we just did, the data from experiment 1 and experiment 2, where B is held steady and A is doubled. We just said that when we do that, the rate is quadrupled. So now we have to set up a relationship between, a numerical relationship basically, between the fact that we doubled A, as you see here, and we quadrupled the rate, as you see here. So now we need to determine an exponent. 2 to the x equals 4. X must equal 2 in this case. This is very simple, right? We have nice, neat numbers to work with. What does this mean about the order of reaction? For A, this means we are second order in A. That's the way that is expressed, second order in A. And that means our exponent here, going back up to the top here, is 2. Okay, so we have dispensed that one, and we can move on to next. Next, we're going to compare experiments 2 and 3. So now we're going to hold A steady while we're doubling B. What happens to the rate when we double B? We just said it a moment ago. If you go back and look at experiments 2 and 3, we double B, nothing happens to the rate. What does that mean? Well, the math here is doubling A equals 1. If we look at that change in rate, it's just 1. So 2 raised to what power equals 1? X equals 0. It's a 0 order reaction, and we can say that this is 0 order in B. So now we know that our Y, going back up to the top here, is 0. This effectively reduces the whole B term to 1. So now we actually have at least the beginnings of a rate law. Very exciting. Rate law is rate equals K times A squared, A to the second power. Guess what? We're done. B is 1. So we have determined the rate law for this reaction. Now let me give you a what if. It would be useful also to know K. So how can we figure out K? Well, there's a very easy way to do this. We pick one set of experimental data. We plug in the numbers. We have A, we have B, we have rate. B has been lost from this expression, so we don't really need it. We have rate from any set of data, as I said. We have A. We can solve for K. I'm not going to do this. It's simple math. You can handle it. Now I want to talk about tackling the same problem, but with a formal approach. The more rigorous mathematical way to set up this equation is what you see here. We're actually setting up a ratio between rate 2 and rate 1. And we're going to use this expression to do exactly the same problem that we just did. And we're going to see that this is not nearly as complicated as it looks. In fact, we are doing exactly the same mathematical operation as we did just a moment ago. Why? Because you need to focus your attention on the fact that whatever is held constant in this expression will cancel. And that makes our life a whole lot easier. What do I mean by that? So what I mean is, here's our data again. And if we're holding B constant, for example, and varying A, certain things are going to cancel out of the expression written here. What things are going to cancel out? Well, notice that we're holding B constant. So this term right here is simply going to cancel. K itself is a constant, so it's going to cancel. And we're basically left with exactly the same expression that we had moments ago. What does this reduce to? Well, 0.008 over 0.002 reduces to 4. 1 over 0.5 reduces to 2. And again, our exponent with respect to A is in fact 2. 2 raised to the second power equals 4. And we can say this is second order in A. So don't let a formal expression like this throw you. And you might ask yourself, well, why do we even need this? The truth is while we tend to present you problems in chemistry that are very neat and tidy, 2 to the second power equals 4, it's not always so neat and tidy when you get in the lab. You may find that your exponents are non-integers. That makes things a little more complicated. You start having to take the log of both sides in order to solve your equation. And there are other scenarios for more advanced problems where you're going to find this more formal expression handy. So keep in mind, it's really not intimidating. It's just setting things up very correctly noting what cancels, and using that to solve your problem. That's all for now.